This is Professor Antonio S. Marahas, and this is Advanced Digital Technique. So, we go now to NOR gate. NOR gate is sometimes called the NOT OR gate. So, it is defined as a gate with two or more input signals, but again, it has only one output signal. All inputs must be low to get a high output, and that is our definition for the NOR gate. Or simply, NOR gate is the opposite of the OR gate. No? So, we have here a symbol of a two-input NOR gate. So, we have an OR gate, okay? And then the output of the NOR gate, it is where your inverter is connected. No? So you have two inputs represented by A and B again. And the output here is A plus B. And the output of your inverter becomes Y, which is equal to A plus B complement. No? Because the complement here represents your inverter. Okay? So this is the symbol for two-input NOR gate. Okay? In other books, the NOR gate symbol is also represented by this one. You have an OR gate and then a bubble. Okay? So the bubble here actually represents this particular inverter. So the output again of this Y is equal to A plus B complement. Okay? That is the NOR gate. Now, how about the truth table of the NOR gate? So you have inputs again A and output B, input B, and then you have an output Y. The combinational values of A, B are 0, 0, 0, 1, 1, 0, and 1, 1. And what will now be our output Y? So based on our definition, all inputs must be low. All inputs must be low to get a high output. So in other words, if A is 0 and B is 0, then the output here is 1. The rest is 0. That is how the NOR gate truth table is obtained. Let's have a 3-input NOR gate. No? So the symbol again for a 3-input NOR gate will be this one. So you have a bubble here, and then you have 3 inputs represented by A, B, and C. So the output Y here will be equal to A plus B plus C. Then you have here a bubble which is represented by a complement. Okay? So this is plus C. Okay? Now, what will be our truth table? So you have A, B, and C. Again, how many combinations do we have here? Since we have 3 input variables, so you have 2 to the 3, you have 8 combinations. You have 0, 1, 2, 3, 4, 5, 6, and 7. The binary equivalent of 0, 3 input, you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Based on our definition for the NOR gate, all inputs must be low to get a high output. So only this condition here, 0, 0, 0, the output here is 1, and then the rest is 0. Okay? So if you notice that this table here is based on the inversion of your OR gate, no? So, di ba, in our discussion in OR gate, if any of the input is high, the output is high, no? For example, in this case, you have 1, 1, 1, 1, and so on. So, in our 3-input OR gate, these are ones here, no? With an input of 1, no? And then this one here is simply 0. That is for a 3-input OR gate. Now, that is the output of this OR gate. Now, once it passes through an inverter, okay, whatever is the output of your OR gate will be inverted. So, for example, in your OR gate, if your output is 0, once it passes through an inverter, it becomes 1. You have output for your OR gate is 1. Once it passes through the inverter again, it becomes 0, and so on. So that is how NOR gate operates.